one hand, I'm very happy and I'm very thankful for the organizers for inviting me here to this university with this very nice island of São Miguel. But on the other hand, I'm a little bit sad because I paid them in a most unfair way. Because this presentation is somewhat of a provocation, I would say. As you can see, by the way, already by the title, okay, the title is supposed to trigger a few things in your mind. So when I started preparing my talk, I remembered, I knew already what I was going to tell you, but the problem is that as I was seeing what I was going to tell you, I remembered a lesson in philosophy in high school. I was 15 or 16 at that time. It was a very, very boring lecture on philosophy, and the professor was talking about the limits of knowledge, which is something that normally philosophy professors like to do. And as sitting there, I had nothing to do, because in fact it was not particularly interesting to me, but a question popped to my mind, which I think popped to all of you at that moment. In particular in my case, because I knew already that I was going to be a physicist, so the question was, well, suppose that I'm really, really a very, very good physicist, and I solve all problems of the universe, okay? What am I then? Okay, if I solve all the problems of the universe, what happens, okay? So the question boils down very superficially, of course, to these two possibilities, okay? Well, if I solve all the problems, am I God? Okay? Or is God beyond all possible knowledge? Okay? Or does a human become a God? So let me just give you a flavor of what this means, okay? So, am I that, or am I this? Okay? You see already that the second choice, by the painting of William Blake, you can see that the second choice is particularly dangerous, because I became a God, but I'm not even able to invent a paper, okay? So, in fact, I decided to go a little bit deeper into this. Okay? Now, there are two possibilities. Option one, the one that I found that was more interesting, is one of the 6 systems of the Hindu philosophy. It's called Sankhya. And in fact, what they say is this: well, maybe there is a God, okay, but there is a problem, because the God that we think about is the primal cause. It's a cause without a cause, okay? Which means that, if you think a little bit about this, what this means is that you can or you cannot attain this God, right? Because what happens, in fact, is that there is, if I find a way of arriving at God, this is a process, so there is a cause to arrive to that cause, okay? So this means, in fact, that this God, which they call Purusha, is beyond all knowledge and cannot be known neither by thought nor by experimental means. So by these means, all we can reach is nature, Prakriti as they call it, okay? And to access this God is terrible for a physicist. We have to give up all thought, rational or irrational, and aim for the primal truth. The best place where I saw this written is one of the oldest and, in fact, most important Upanishads, the Isha Upanishad, and they say, as you can read quite well, this: know that all this, whatever moves in this moving world, is enveloped and enveloped by God. Therefore, find your enjoyment in renunciation. Do not covet what belongs to others. Okay, so end of the story. There might be one, but we cannot reach it by physical means. The second one is more interesting for humans. Okay, and if we think that we really can understand everything in nature, then at some point we should ask ourselves the question, well, let's try to be God and see how it goes, okay? And the first attempt of this was by Euclid in Catoptrics, around 320 before Christ. This one was not a very good one. The second one was much more interesting. It was the proposal of Herod of Alexandria in 60 of our era, and he tried to explain reflection. Okay, so what was his problem? So we have point A, we have point B, there's a mirror here, and we want to make light to lead from A and arrive in B. Okay? So what are the conditions for this to happen? So Herod had a fantastic idea. What he says, well, let's try other possibilities and see how it goes. Okay, let me try to play God. Okay? And so what he did was very simple. Well, let's first see how nature does it. I have a mirror, I know that angle of incidence is this one, the angle of reflection is this one. Let's suppose, as nature does, that this angle is equal to this angle. Okay? So he made the following. He didn't know much about algebra, so he did the geometric constructions that the Greeks like to do. So I just put the point A in reflection on the other side of the mirror at exactly the same distance. So you see these and these are equal, these and these are equal, so this angle is equal to this angle. And since the angle of reflection is equal to the angle of incidence is equal to the angle of reflection, this angle is equal to this angle. And this can only happen if this is a straight line. Okay? So what you see that what nature does is that it draws a straight line from point A to point B. Okay? Now let's play God. Okay? So if I play God, I choose another path. Right? So now I chose this one. It also goes from point A to point B. But you immediately see the problem with the construction, right? This one is equal to this one is equal to this one, but this angle is not equal to that one. I left the previous one so that you see now that there is a triangle here. Okay? And what happens is, as is well known, the sum of the two sides is bigger than that one. So it seems that indeed, if we play God, then we discover something extremely interesting. We know that the straight line is the shortest path between the 2 points. So what nature does by choosing the angle of incidence equal to the angle of reflection is just to say we're choosing the shortest path between 2 points. Okay? So, success. If we decide to play God, then, and know of course as he does, that line only follows the shortest path between 2 points, then we are able to reproduce the laws of nature, that is, that the angle of incidence is equal to the angle of reflection. One important remark for what follows next is that for light, the shortest path is also the path of least of covering this distance by least time. Okay, so in fact, shortest and least time, shortest distance and least time are two possible ways of looking at this problem. So this continues. In fact, people forgot more or less about Heron's idea until the 17th century, where in 1662, Pierre again, in a book, Analyse des réfractions, he finally writes the principle I'm talking about here in the way that we more or less know it today. Nature operates by the simplest and most expeditious ways and means. Okay, this is the principle of reflection, but it's of course a little bit vague. We don't know how to apply this in general in most cases, because for that we need to know what is simplest and most expeditious, of course. Okay, but this triggered many reflections about this point. We can try to play God. We can try to see how we then choose if to play God. We have much more freedom. And how do we choose what really happens? And in fact, the idea took hold, and by the mid-1740s, the method gained momentum, and many people were thinking about this. So in particular, the usual suspects, Euler and Montgomery, they were applying this to mechanics in particular, but also to optics. And on the mathematics side, there was also people playing a little bit with this, the twin brothers Bernoulli and L'Hopital. And in their case, what they were trying to find is extreme of function basis. For instance, surfaces of less curvature, least curvature, or curves with least distance between 2 points. But the real thing started a little bit after that. But although the original idea was even before the one of Euler and Caprice. So this gentleman here, so Jean Balabert, he had a fantastic idea. Okay, let's really play God. Okay, so he tried to apply, as physicists always do, to the simplest of cases. So he went to statics. Okay, so statics is the most simple thing that any physicist can do. That's why we did it for engineers. And in fact, what he said is this. Well, suppose that I have a system of forces in place, okay? And this system of forces can produce some movement. They don't exist, in fact, in practice. But let's imagine that I could indeed have this movement, Okay, they do not exist in practice. I can only imagine them because I'm God. And because of this, he called it virtual displacement. Okay. Now, in physics, there is a concept which is very, very important. It's the concept of work, which measures basically how a force can produce a given displacement. Okay. And this concept comes from the projection of a force over the distance that you can go along the path. Okay? So you see, if I choose different paths, I have different projections because the path goes along this direction of the path. As I project, okay, I get different values for the work. Right, so the work for a given path is, just for you to understand, is this. Okay? So how do I disentangle between all these possible paths? Okay, and João Seixas came to a fantastic result, which is called the principle of virtual work. And this principle only tells this. A system is in equilibrium if the virtual work corresponding to a virtual displacement is null. Okay, so a force in the right path just produces zero virtual work. So I can imagine all the paths, but nature chooses the one which produces zero virtual work. Okay? So this is the first approach to the problem, and then you went, of course, to the second one. Okay, now I solved the problem of statics, now I go to dynamics. So I'm observing some object fall. Okay? And at a given moment, when this object passes at a given point, what happens is that the platform in which I was standing just simply drops. And I start falling exactly like the object is falling. Okay? So what happens at this point? You might not have this impression, but if you're falling with an object, you don't see any force on the object. Because what happens is that you have the gravity force, but you're in an accelerated frame. So what happens is that there are initial inertial forces. And so the sum of the inertial plus the weight forces are zero. And guess what? I'm back to statics. Okay? So since I'm in statics now, I can use my principle, right? So I can try to find all possible paths, okay? All possible paths and try to calculate the virtual work for these paths, okay? And of course, the one solution is, of course, the one. Now it cannot be only the applied forces, like because the body does not have only the weight applied. So now the virtual forces, the total virtual work of applied forces plus the inertial forces must be zero. Okay? And this is fantastic because this is the most general solution of Newton's equations. The most general solution of mechanics is, in fact, this principle of Waldo. So again, the virtual work is zero. This guy for sure had to tell this very quickly, otherwise it would be delayed. But the interesting thing is that this triggered a new line of thought which was created by two people, so Lagrange and in fact Hamilton, and it boiled down to what we now know as variational principles. We invented something called an action, and the path chosen by nature is one which minimizes the cost. So the action is a cost for a given choice, and in fact what happened is that this action is the smallest one for the path that is chosen by nature. So this is a very interesting approach, okay? But of course we know that at the atomic scale or below, we have completely different behavior. Okay, so the question that many of the people who started to study these phenomena at the atomic scale or below, okay, one of the things they ask themselves, of course, is very simple. Can we still play God as Mr. Waldo told us to do? Okay, and the answer turns out, it took many years to find this answer, but the answer is yes. But of course, according to different rules. Okay? And in quantum mechanics, if we want to go back to our the way that humans normally refer to gods, okay, I think the best one is this phrase. And it's the one that mostly can be applied to quantum mechanics out of all physical theories. The gods love what's mysterious and is like what is evident. And quantum mechanics is an example of this more than anything else. Okay? So let's see what quantum mechanics tells us. So I'll put this in terms of what would be the sutras of quantum mechanics. Okay, so these are the postulates. And the first postulate tells this: the state of a system. The state of the system is represented by a mathematical entity which we call cat. You will see later on why. Okay, and which we write this way. You see, vertical bar, ladder, and greater than psi. And this is a state. In quantum mechanics, what we have is states, which exist in the space of all states, all possible states, and contains all the information concerning the system. Now, why did we change into this when we went from classical mechanics to quantum mechanics? For a very simple reason, is that in classical mechanics you only have to give position and velocity for a body, right? But once you go to quantum mechanics, you have to give position, velocity, parity, spin, whatever you want, okay? And all this is encoded in this object, this cat, okay? Now, the second thing is, furthermore, as you all know, at the quantum level, all systems have a double nature. So they have a wave, they are either a wave or a particle, depending on the experiment that you're doing. This is called duality. As a consequence, this quantity, this ket, must also convey this information, right? So this is what the ket, or the wave function, if you want, does for us. But then the second question is, of course, I have a complicated object, how do I extract information from such an object, since it has everything in it? So the answer is this, is postulate 2, and it tells that every observable attribute of the system is represented by an operator that acts on the cats that represent the state of the system. So what does this mean? Well, an operator, in fact, is a mathematical apparatus. And this mathematical apparatus is what is representing the physical quantity, okay? And this operator just does this, it gobbles a cat, transforms, just spits a number, and expels another cat, okay? Just this, nothing more than this. And so these operators are what are the objects which are going to operate on these mathematical objects, provide a number of what we want to see, and give another state for the system. So, in particular, a measurement is represented by an operator because it affects a cat, which represents the physical object, okay, extracts a number and gives something else, okay, so this is what it is. Now, this is extremely important. If you took nothing else from my talk, this is the important point. And I'll ask my chairperson to give me just 20 seconds to show you this. Operations are in general non-commutative. The problem is that you have been told since early primary school, okay, that multiplication is commutative, addition is commutative, everything, right? So just let me show you that operations can be non-commutative, okay? Just imagine this one, which you all know by now, right? So, and suppose that I have my axis, x, y, z, okay? Z, x, y, okay? Suppose that I make first a rotation around the x-axis, okay? And then do a rotation around the y-axis. This is the final result, right? Now let me do something else, okay? So I first do an operation around the y-axis, okay? And then I do an operation around the x-axis. You don't write the same thing, right? So these two operations are non-commutative. So this is one example of this non-commutativity, and this is very, very important. Why? Simply because measuring the position and then the velocity is not the same as measuring the velocity and then the position, and this is the basis for the Heisenberg uncertainty relations which you all heard about. Okay? So the uncertainty relations which tell that I cannot measure position and the velocity with the same precision is an immediate consequence of this fact. Okay? Now, postulate 3. The only possible result of a measurement of an observable O, or quantity O, corresponds to a value, this little O, associated to a state that remains unchanged by the operation of this operator O. Okay, so that it gobbles this state, psi, just sends away the state psi, the same state psi, and provides a number. And these are the only things that we can measure from the point of view of quantum mechanics. What is the problem of this? Well, actually, this postulate is what is at the origin of the word quantum. Okay? Why? Because, for instance, the energy operator, in some cases, do not have a continuum set of values. Okay? For a hydrogen atom, for instance, what you see is that the values of the energy are discrete numbers, that is, numerable numbers. Okay? And how do I see this? It's not just a mathematical game. If I take, for instance, the hydrogen atom and just give energy to this atom, it's known since the 19th century that it produces lines, okay? And these lines are discrete in number. So this is not a mathematical game, this is observed in nature, okay? And this is one of the examples of that. The second thing about, the fourth thing about the quantum mechanics is, this is also very, very important, is that when the measurement of an observer is done, then what happens is that we don't get also, like in classical mechanics, in which you say, this is going to happen. No. What quantum mechanics tell us, it is also backed by a huge amount of experimental data. What you get is the probability for getting a result. Not the result, not the 100% probability of having something, but the probability for that to happen, right? So let me tell you what is this. So what is the main difference between quantum mechanics from this respect and normal physics? The first one, which I don't talk here because it's a little bit arcane in this context, is that the probabilities in quantum mechanics can become negative. This is the first one, and it's perfectly normal, okay? The second thing is that as I do the projection of the initial state over the state, the so-called eigenstate, the state that stays the same under the operation, as I do the projection, then something very funny happens, okay? So what happens is that I have my initial state, the measurement makes the projection over the state that can be observed, right? The square of this quantity here is the probability. Now, if I say it like this, it's not really very serious, but suppose that I say that I want to measure, I have two possible results, and I measure this one or this one. The problem is that the square of the sum of two things contains the square of the first, which is a probability, the square of the second, which is also a probability, but then I have the cross term. Now, in optics, this is known what this gives. This gives interference. Which means that, for instance, I have a state, which is an electron. I ask myself whether the electron will pass here or there, and I have the probability to pass here, the probability to pass there, and the probability cross to pass by the two at the same time. And if you think that this is not backed up by experiment, this is a real experiment. So I have an electron source, two slits, and then what I observe is not only two regions, but a whole series of regions, as you see here, which is a typical pattern of interference. Now, what is curious is this. So, coming back to our friend, God, so the question is that quantum mechanics, as you will see, it's a funny probabilistic theory, okay? And it seems that you're playing dice with God, but you should get used to the fact that He decides who wins. I have no control of who wins, okay? He decides, which means that He has a very nasty personality. So that's why I was saying that at the beginning that the psychology is a little bit dangerous. So let me just finalize the postulates, and this is one of the most unpleasant postulates, again backed up by experiment. Immediately after the measurement, the state of the system collapses to the particular state associated with the measurement outcome. So the measurement is an operator, gobbles a cat, provides another cat, right? And immediately the state just collapses to that one, and I never see the other one. Okay? This is shocking, I should say, and physicists have a really, really bad time trying to solve this. The second very unpleasant thing is that what is again unfair, that is, it takes this one, projects it over this one, but if I perform the same measurement again and again and again, okay, it always provides the same result, despite the fact that quantum mechanics is a probabilistic theory. It provides the same result with 100% probability. Okay? So if he wins, he uses the same trick to continue winning. Okay? So it's not very nice. So one such example is the Stern-Gerlach experiment, which we can discuss later on, but this is an example. I take, for instance, silver atoms, okay, send them, pass them through a magnetic field. There will be two lines corresponding to two types of silver atoms. This is unclassical completely, and what happens is that you will see two different values for this system. What I was saying is that if I put another Stern-Gerlach experiment after this one, stop this beam here and continue on that one, I will always get only one beam. But if I have another Stern-Gerlach experiment rotated 90% with respect to this one, then you see again the separation into two. Fine. I stop this one and I get this one only, right? So I put again a Stern-Gerlach like this one only on that one, and guess what? I get two again. Right? So I cannot tell you more about God, but sometimes it's really unpleasant. We have to deal with him anyway. So the sixth one is an important one. It's not important for us here, but it tells that the time evolution of an operator or an operation is given by an evolution operation, the operator also. So there is an operator to act on operators. Okay? This is not important for us, but that's why I told you that quantum mechanics was a funny probabilistic theory. Because I think he's really laughing up there. I mean, because he makes us completely confused, right? What it tells is that we have a probabilistic theory, but the time evolution of the probabilities is deterministic. You see, this is, I mean, it is really, I'm sure, laughing at us, he or she, I don't know, laughing at us from up there. So, can we really do like Mr. D'Alembert? Yes. The difference is, in classical physics, we can explore one part at each time, and this is important for what I will tell you in the end of this talk. But the difference is that in quantum mechanics, we can have all paths explored at the same time. Right? This is superposition. And because of this, I mean, the state is not only a state, it's a superposition of states. Okay? And so, in fact, all paths can be explored at the same time. And in fact, we cannot choose one path. We can only say which path has the highest probability. Okay? So the cost of a given choice is related, in fact, to the probability. Now, what is the consequence of this? Well, we can play God, of course, right? But we have a problem because the number of hands that we have to deal with is potentially infinite. Which means that we can only win the game in a limited number of cases. So take-home message, playing God is dangerous, especially if you're not the real one. Okay? So beware, because quantum mechanics tells you something interesting. So let's go to the end. What has this to do with, for instance, computers? Now, what is a computation? What you have in your mobile phone or in your tablet or so on, you have a computation, and the computation is an operation on strings of bits that gobbles a string of bits and provides another string of bits. Okay? The problem with classical computation is that this operation can only be distributed by a number, it can be very big, but it's always finite number of machines. Okay? And this is what's happening now. I mean, when you take a computer, you see a core 5, a core octa-core, or something, or tetra-core, or something like that. That means that you have several machines inside one CPU, and they are working in parallel. But this number is finite. Okay, so can this be improved? Yes, with quantum mechanics. Okay? So a quantum computation is exactly the same. It's a computation that is an operation on a string of qubits, okay, that provides another string of qubits, right? But what is a qubit? The point is that classical bits are either 0 or 1, okay? Now we are in quantum mechanics, so we can construct objects which are at the same time 0 and 1. 0 with a given probability, 1 with another probability, okay? And the qubit is this superposition, and we can construct multi-qubit states. right? Which are quantum states. And now, quantum computation is very simple. It's just an operator that transforms an initial quantum state into a final quantum state. Okay? So why do we worry about this? Because of the properties of quantum mechanics, which can explore all possible paths between input and output, right? Which means that it can create potentially an infinite parallel machine. And now you say, why is this important? Well, in many cases it's not important, but it happens that many classical unsolvable problems become solvable in quantum machines. One of them, which should worry you quite a lot, is prime factor decomposition, the so-called RSA algorithm. Why is this important? Because each time that you go over the net and buy something, you use this algorithm for cryptography. This little thing that appears in your browser, right? So these will disappear with quantum computers. Okay? Now I see that you're becoming serious. Now, we can discuss that later. This is possible if quantum coherence is maintained, but I should warn you that this will appear in your homes in around more or less 10 years. Okay, so be prepared for that. But is encryption lost? No, and I tell you why. Because we have something that was invented by Mr. Werner Heisenberg, and which is very, very nice. The question is this: suppose that Alice is talking with Bob, and in the middle there's someone trying to see this quantum channel, okay? So the quantum encrypted information, and tries to find out. The problem is that if you perturb a quantum system in an unforeseen way, what will happen is that we know now that will destroy the quantum communication channel, and what is worse, because of quantum mechanical properties, you also show who this drop is. Okay? So there are now already companies like Idecontic, which in fact sell this product to the public. Okay? So it's already something that exists. It's not science fiction. So let me finish. Sorry, I think I took a little bit more than. But so, what is the message to take home? That variational principles, so these minimum principles, are essential tools for physics and engineering. The new quantum technologies are indeed behind the corner, okay? And I think one of the speakers here will for sure delve into this problem and will affect our daily life, okay? Not only in computing, probably not so much in computing, but certainly for communication and security. Okay? So quantum mechanics is something that we have to learn for the future. Okay? And the final question, of course, like the one that I started, is what will happen when they'll be in place? And my answer is very, very simple. Nobody knows. Okay? So there is no escape, okay, because of what I told you, there is no escape for continuing to play God. Okay? Because we need to do that in order to be able to tackle these problems. And this, despite the fact the opponent certainly wins most of the time, okay, but there's no choice. We need to continue to do that. Maybe I leave you, since this is a particular community, I leave you with some food for thought, is how much this will affect social science. Okay? And this is something that I hope at the end of this Congress, you will find a solution for this. Okay? Thank you.